So we have completed the second unit. We're diving into the lecture behind Unit 3 today, but we've had a little bit of practice with this, specifically if you are in the Tuesday lab section. So we can connect some dots between what we observed in lab or will observe on Friday and the theory underpinning some of those observations. So let me grab our notes. And I'll start sharing in a minute. Let me just get rid of a couple of tabs that I don't need. Okay. It's better. All right, so PowerPoint, here we are. Okay, so our third unit is unsurprisingly going to build off of what the groundwork that we laid in Unit 1 or Unit 2 actually. And it is going to give us an opportunity to sort of inspect the other aspect of the electromagnetic force. We spent 4 chapters talking about electric fields and then figuring out how, let's say, a charge or a group of charges could produce a charge distribution that's either made up of discrete point charges or it's continuous. We talked about how to produce I guess I should say the benefits of using a capacitor to produce an electric field that had a known orientation and a known strength. We're going to kind of shift gears here and start working our way toward understanding the same type of aspects, but for the magnetic portion of the electromagnetic force. So we can start off with a device that we've seen before. Here's our capacitor, and we are imagining that it's already started off charged. We talked some near the end of the second unit about how this capacitor becomes charged if you connect it to a battery or some other source of potential difference. But once that capacitor is charged, we know that there's energy stored within the electric field between the plates, and we can use that energy at some later point in time. So to phrase that another way, you can save it in the as potential energy and then use it when you put the capacitor into a circuit or something like that. So if we imagine here that our capacitor starts off charged and we have not yet connected it to anything, the charges that are on the plates of the capacitor are not free to wander around. So in other words, the sea of electrons that we can imagine existing inside of the battery, let's say, and inside of the wires that make up this circuit, it's shifted and then come to a stop. So these negative charges are as far away from one another as it can get. I can say the same thing for the positive charges. And if we set this up and make a simple circuit here, and this is the simplest possible type where there's just one wire that connects the 2 plates of our capacitor, now those charges have more space over which they can spread themselves out, and they'll take advantage of that. And over time, the amount of charge on any one of those surfaces is going to deplete. And we should be able to find a time where all of the charge that started off in the plates of the capacitor has depleted, has gone away. So when I say gone away, what we are not doing here is taking charges out of our system or adding more charges to the system. We're simply just rearranging them again. And if we kind of think about this capacitor from like the biggest picture sense or like the broadest sense, the capacitor is neutral the whole time. All we've really done is taken the negative charges and separated them from the positives so that there's a potential difference between the plates. But I started off with exactly the same number of negatives, exactly the same number of positives. So as a whole, this capacitor is neutral. What we are concerned with in this part of our conversation is what actually causes these charges to split or to spread themselves out on the 2 plates of the capacitor initially, and what happens to these charges when the capacitor is connected to some sort of simple circuit, and they have the ability to start moving again. So here's the same scenario, or our same like discharging capacitor. And what we are looking for here is the concept of some sort of indicator. So something that we could use that's just not an ordinary ammeter to confirm that charges are actually moving through that wire, or in other words, that charges are depleting from the plates of the capacitor. So one that is something that we didn't actually investigate in this lab, but we will see in maybe 2 labs down the road, maybe 3. What we will be able to, or what something that we can use as a device that will indicate the presence of current or the absence, will be a compass needle. And this kind of touches on a larger conversation. So if we think about the primary use for a compass, we probably imagine trying to navigate and using the planet's magnetic field as an indicator so that we know if we are heading north or south or anywhere in between. There is another magnetic field that is the result of charges moving through a wire. And this magnetic field is temporarily going to be kind of large in magnitude compared to the planet's magnetic field. So this compass will actually stop responding to the planet-wide magnetic field and instead be influenced by the magnetic field that is the result of this current-carrying wire. So you would see the needle deflect, but once the capacitor was discharged, then there's no current in the wire. That means that the compass would go right back to responding to the planet-wide magnetic field. And this is a conversation that we're going to come back to later on in this unit. Actually, I don't recall what the chapter numbers are in the newer edition off the top of my head, but the electromagnetic induction chapter. I think it's the 4th one in our group of 4 chapters in this unit. We're going to talk about how comparatively weak the planet-wide magnetic field is compared to the magnetic field that would be produced by this current-carrying wire, or the one that would be produced by one of the magnets that you might have on your refrigerator. So the planet-wide magnetic field is obviously very large in scale, but it is weak enough that a compass needle can respond to, or I guess be overwhelmed by, the magnetic field coming from some other kind of ordinary source. So in the absence of an ammeter, if you had a compass needle, you could tell whether there was current in this wire or not. It would be a little trickier if you wanted to figure out the direction of the current in that wire, but not impossible. And then another indicator that you could use is the actual temperature of the wire. And this kind of brings us back to some conversations from the first semester, namely when we were talking about the law of conservation of energy and I guess telling the difference between mechanical energies and thermal energies. And one of the, or I guess the biggest difference that you are probably thinking back to is how thermal energy can be produced as the result of either or some combination of positive and negative work that one object is doing on another, or one force is doing on some object. And the classic example would just be to rub your palms together. There's no way that you could rub your palms and end up with one of them getting warmer, but the other one staying the same temperature, or the other one getting cooler. They have to warm up together. And while it is a good starting point to think about a current carrying wire as functioning similar to a hose that has liquid in it, there are some differences here. We're not really thinking of a current carrying, or it's not really adequate or accurate to model a current carrying wire as if it's hollow and charge carriers are just moving through it. In reality, there are charges that are already native to that wire, regardless of whether that wire is connected to a circuit or not. So when there is a current moving through that wire, instead of thinking about our charge carrier as something that's moving through a hollow tube, think of it as a chain reaction. So a bunch of elastic collisions that the charge carriers undergo with all the other materials in the wire. So we wouldn't be tracking a single charge carrier. So if we take this back to our capacitor, we wouldn't be tracking a single electron as it makes its way off of this negatively charged plate and then goes counterclockwise through this partial wire loop. But we would be tracking the effect of one of these electrons that begins on the negative plate, kind of transferring its energy to the charge carrier directly in front of it. So like I mentioned, there's more to that story that we're going to kind of come back to in the second half of this chapter. Let's think about, or I use the term charge carrier, and I don't recall whether I used that term in the second unit or not, but we can relate this back to the imaginary charge escalator model that we use to understand how a battery can charge a capacitor. So in that case, we were imagining that positive ions were climbing up an escalator so that when they got further away from the negative terminal of the battery, the amount of electric potential energy each one of those ions would have would increase. And then by the time it actually made it to the positive terminal of the battery, we could think of that charge carrier as something that had a bunch of electric potential energy that it could then turn into kinetic energy. But by the time that charge carrier made it back to the negative terminal of the battery, after going through the wire and the light bulbs, whatever it might be in your simple circuit, by the time it gets back to the negative terminal, all of its potential energy has been lost. So it's all been turned into some combination of kinetic energy and thermal energy. So the heat or the warmth that you would be able to detect in your current carrying wire. We know in reality that the positive charges are not actually going anywhere. They're locked into like a lattice or into a specific shape or orientation, sort of similar to the way that we thought about how an insulating material could be polarized by some external source charge. You're not actually separating the negatives from the positives in the case of the polarized insulator. But for a conductor, it's really easy to get the sea of electrons to shift when you have some external point charge or a chargeable rod, if you think back to the electrostatics lab that we did the week before last, I think, or maybe 2 weeks back. So the idea is, or the point that I'm making here is that the negatives are the only charges that are actually moving. But we can think of the current produced by a negative charge that's headed, let's say, clockwise through a loop, as being the same as the current that a positive or a group of positive charges would have if it moved through the same circuit, but in the opposite direction. So what's really happening on the interior of any one of these, this would be an example of a conductor here because our electrons are not really tightly linked to the nucleus. Instead, they're free to move around or to kind of wander through the interior of the material. What's actually happening here is that these negative charges are capable of undergoing a bunch of elastic collisions with each other and with these fixed stationary positive charges. And if memory serves, so conduction electrons, we can tie this back to the concept of a valence electron, the ones that are the easiest to remove from an atom. These are the ones that are going to make up the sea of electrons that can kind of wander through the interior of some conductor. So we know that in reality, our charge carriers are conduction electrons. But again, if we know that each one of these electrons is heading, let's see if I can find, so like this one here is a good example. It's heading in the positive X direction primarily. I can model this current or model the current produced by this conduction electron as being identical to one that would result if I had a positive charge that had the same magnitude but heading in the negative X direction. So this is the concept of, or this is kind of leading us to the concept of conventional current. So I don't want to jump the gun here, but I do recall mentioning conventional current when we were talking about the charge escalator model in the second unit. We're imagining that the positives are traveling forward when in reality we know negative charges are traveling backwards. So that kind of leads us to 2 different types of current or 2 different ways that we can model or understand the current that shows up in our current carrying wire that's connected to our charged capacitor. The first is electron current. That's exactly what it sounds like. And the positive charge current, or the current that we can imagine being similar to what would happen if positive charges were actually moving, that's conventional. So we're looking for some rate, the number of particles that can go through either a certain section of circuit that might go through an ammeter so that you can get a measurement for the current. But we're looking for a number of particles per unit time. If you had Lab Tuesday, then you're already kind of familiar with the concept of using an I to indicate current, so the flow of charge. And for electron current, we can distinguish this from conventional current by just defaulting to a negative, or not a negative, but a lowercase I. So lowercase I sub e, we are looking at the realistic representation of what the charge carriers are doing. So the positives are fixed in place, the negatives are heading in a certain direction. If I can count up the number of negatives that pass through any one piece of a circuit or that pass through an ammeter, let's say, per unit time, then the current is just going to be something that I can write as the number of charges per unit time. So since you are not likely to be able to hone in on just one electron and kind of watch its effect as it kind of affects one end of a wire and then see how that results in some change that you can measure on the other side of the wire. Since we can't just easily aim a motion sensor at that or get a direct observation of this one particle that's moving, it is easier for us to measure or observe the current that's moving through that wire section and kind of backtrack. Because if we know the magnitude of the current and we know how much charge each individual charge carrier contributes, then the product of the amount of current and the amount of time that she waited should give us the number of particles that actually pass through that point. So and this capital N here is just meant to represent the number of something, in this case, electrons. So if we're imagining that this little disembodied piece of wire is initially not connected to a capacitor or a battery or something that's going to actually push charge through it, then there is no relative motion for the particles inside of this, on the interior of this wire. They are in an electrostatic scenario, just like the plates of the capacitor. But if we imagine that we're looking now at a cross-section of this wire and it's connected to some source of potential difference, then the particles that we're actually tracking, kind of moving through the wire, are, like I mentioned, not legitimately going through the wire the way that water would go through a hose, or the way that maybe a ball bearing would move through a tube. All they really have to do is transfer some momentum to the particle directly in front of them. Then that particle is going to transfer momentum to the particle in front of it, and so on. So we can think of these individual electrons as being kind of the source for the reason why the sea of electrons that we talked about in Unit 2 is actually capable of shifting. It's the combined effect of all of these individual particles that cause this kind of macroscopic structure to respond to, I think nudges was the term that I used at the beginning of Unit 2. But now we know that if these electric charges or their charge carriers that are moving have negative charge, we can manipulate them just by introducing some other electric field. And the electric field that is ultimately responsible for producing the electron current and, by default, the conventional current as well, that is something that we're going to kind of dig deeper into in today's lecture. So I want to point out here, let me pop, oh, hold on. Something, I don't know whether WebEx looks a little different for you compared to Monday morning, but something about it has changed and it's a little bit harder, or I can't get to the chat in just like one click instead of two. So I'm going to keep this open and I'll keep an eye on it. But if you ask a question in the chat that I don't initially see, just hop on the mic and let me know about it. But to kind of get back on track, we can think of these individual charge carriers as just being required to transfer some momentum to the particle directly in front of them. So what we're not really doing is tracking a single electron as it works its way all the way through some section of wire. But we can make sense out of what's happening to these particles by evaluating the drift speed. So this is kind of akin to what you would hypothetically be able to measure if you could put a motion sensor inside of this wire and just tell it to track a single charge carrier. And if you think about how quickly, let's say if you were to turn on a light switch in whichever room you're in now, if you think about how quickly the light or how quickly you observe light coming from the lamp or the overhead, the light bulb, whatever that you turn on, you don't have to, or you really can't really distinguish the amount of time between when you flip the switch and when you see the light. It seems like they're happening instantaneously. And in reality, they're not instantaneous, but they happen over a really small time period. So that's why this drift speed being as slow as it looks, so 10 to the minus 4 meters per second, that seems like that's counterintuitive. It seems like it suggests that if you were to measure the length of all the wires that are, let's say, connected to, I've got a desk lamp here. So if I were to measure the length of the wire and figure out how long it would take for a single electron to traverse that distance, I should be waiting a really long time, or a much longer time than when I actually observe, to actually see the results of turning on my desk lamp. It shouldn't look like it happens instantaneously. But this, again, just kind of harkens back, or it dovetails with the idea that we're not waiting on any one individual electron to go all the way through all of the wire in your circuit. All you needed to do is traverse the small amount of space between it and its nearest neighbor and to transfer some momentum. So if we imagine taking a look at the interior of this wire so that we can understand, I guess, why these charge carriers start to move in the first place, and then we can balance that against the concept of electron current that we saw in our previous slide. What we would have to take into account, or what is kind of easy to overlook at first glance, but is something that we need to think about, this electron, or this wire segment is already full of electrons. So I have to have some sort of way to characterize or to quantify the number of electrons I would expect to find per unit volume for because a wire is actually three-dimensional, but the current is going to go from end to end. So in other words, I'm never going to find a current that goes from the lower portion of this wire to the upper portion. It would just be aligned with the x-axis like we have here. So we can compute a linear density kind of similar to the way that we thought about the linear density for a string when we were talking about waves in Unit 1. We knew that in reality, the string had 3 dimensions, but since our wave was going to be propagating from one end of the string to the other and not the top of the string to the bottom, we were able to just get away with measuring or evaluating its mass per unit length as opposed to its mass per unit volume. And we want to think about the wires the electrons that are already in these wires exactly the same way. So if we know what the wire is made up of, and I thought I had a different kind of thing showing up here, but if we know what the wire is made up of, we can define this lowercase n sub e. So capital N was actually the number of electrons that existed in, or that moved past a certain point in the circuit, but lowercase n sub e is just an electron density. So the number of electrons that I would expect to find per cubic meter of wire. So imagine that now we've let these charge carriers move a little bit. So in other words, we've switched on our light bulb or whatever, and now current is moving through this circuit. So to think of this another way, the imaginary escalator that we can visualize inside of the battery has now switched on. So it's pushing charge toward the positive terminal. It's pushing our imaginary positive charge carriers toward the positive terminal of the battery. So if we wait some interval delta t, we'll be able to track how far any one of these electron charge carriers has moved in that time interval. And again, since the drift speed is really low, the displacement that one of these electrons would undergo will be really modest. But as a whole, the sea of electrons will undergo a larger shift. So when the combined effect of all of these individual electrons shifting a little bit in one direction is kind of considered, then you have this displacement that we can indicate at, or that we can, indicate with some delta x. So we're imagining our charge carriers are moving from left to right here. If we can measure the cross-sectional area of this wire segment, we can do two things with that. So one, we can calculate the volume contained within this cylinder, because the area of the cap of a cylinder times its height gives you the volume. And in this case, the cylinder is laid on one end, so the height is just our delta x. And also we can figure out from the electron density how many charge carriers would be capable of moving through this space in this time interval delta t. So if this is our t initial, or t0, I guess, at the beginning of this scenario, after we let some delta t elapse, a certain number of electrons have moved through that displacement. And we can use that to figure out the number of electrons that have actually moved through that section. So in other words, if you wanted to come up with some way to just kind of focus on a single electron as it moved from one end of the wire to the next, it would be a bit of a challenge, practically, because if we think about our motion sensors, they can't detect the motion of just one particle, but also it would be difficult to kind of hone in on one charge carrier at a time. But what's not difficult is to determine the electron density for a specific material. So this is a characteristic, or like a property of a material, the same way that mass density and like specific heat are properties of a material. So if we know that our wire is made out of copper compared to aluminum or steel or something like that, we can get a pretty good estimate of the number of available electrons to start with. So that once we calculate the volume of this small cylinder, the actual number of electrons would just be the product of the electron density and the volume. So since electron density is going to be measured in particles per cubic meter or per unit volume, you just end up with the number of particles when you take the product of these two quantities. So now we want to take a look at the relationship between the actual volume of this cylinder and the drift speed, V sub d. So our electron number density is our lowercase ne. The volume I can express as the cap area times delta x. And this delta x is something that I can write in terms of the drift speed and delta t. So it's not immediately obvious when you first look at this, but the product of this electron density and area, a drift speed, and a time will just get you a number. So everything is going to cancel out. We have our area multiplied by the distance, like the delta x that exists in our expression for V sub d. That's going to cancel out the density that showed up in the denominator of lowercase n sub e. Then I've got a delta t, and what is left over? So the delta t comes from the delta t cancels out the second that's in the denominator of the drift speed unit. So I just have a number, something that's completely unitless at this point. Now, since I'm concerned with the number of electrons that actually pass through some certain wire segment, but I don't really have an easy way to directly measure a single electron compared to measuring the electron density of the material that makes up the wire, and then measuring the physical dimensions of the wire, the product of the electron density, the cross-sectional area, and then this average drift speed should give me the number of electrons that pass through that section of a circuit every second. And I don't think that I noted this actually on the previous slide when we were first kind of introduced to the concept of electron current. This here is just number of charges per unit time, But if we know the charge that each individual charge carrier contributes to the sea of electrons, we can turn that current into something that we can express in amps, which is a coulomb per second. So this shows some common electron densities for different conducting materials. So these are things that you might want to go to if you were asked to design a specific type of circuit and you had the ability to produce or to choose from wire that's made out of different materials. And this here kind of highlights why copper wire is so valuable, or why it's so useful in producing circuits. Each copper, or I should say like each unit volume copper wire contributes a relatively large number of conduction electrons compared to other metallic materials where there are conduction electrons available, but just not in as large numbers as you can get if you kind of choose wisely. So copper and iron are about the same effectiveness here. They have about the same electron density, but this is something that varies with material. Okay, let's backtrack here. See, it looks like we're okay in the chat. Does anyone have a question they need to ask on camera before we push this a little bit further? Okay, jump in at any time. So let's think back to our charged capacitor that we can put into some sort of circuit so that we can allow the capacitor to discharge itself. Now we saw that a typical drift speed is a lot smaller than you might think if you just kind of go through the thought process, or or actually you can conduct a real experiment by just switching on a lamp and noticing that you see the light almost instantaneously. So how do we make sense out of this really small drift speed and the comparatively short amount of time that you have to wait to see the effect of you turning the switch? So let's say that this particular capacitor is charged so that you've got plus or minus 16 nanocoulombs of charge on each plate. Those charges are stationary until you connect the plates with some wire or something that can conduct and allow current to flow through. So now, oh, and I should say the values plus or minus 16 nanocoulombs, those are chosen so that we have a number, or we have a ballpark idea of the number of electrons that had to have been stripped off of one plate and taken to the other to achieve this charge distribution in the first place. So that's around 10 to the 11. So each one of the negatives that, let's say, starts off on the surface of the negatively charged plate of the capacitor, in order to make it all the way through this 20 centimeter long wire, we can just use our definition of speed going all the way back to probably day one of semester one. We know the speed from our, that was given a couple of slides earlier. If the length of the wire segment is 20 centimeters, which is pretty modest, this should take about 2,000 seconds. So that is somewhere between an hour and half an hour, 2,000 over 3,600. So that's like, yeah, like 33 minutes or so. And you don't have to wait 33 minutes for a light to switch on. So we can make sense of this discrepancy by thinking about, or by just kind of looking at one small slice of the wire at a time. And again, realizing that that wire is not really like a straw or something that starts off empty and then has or allows something to move through it. It's more like a garden hose that you don't empty out between uses, so that when you turn on the water, you don't have to wait for water to make its way all the way through the hose before you can actually see the evidence of it and use it to, water your lawn or whatever. You wait a much shorter amount of time if you leave some water in the hose, because all you really need is for the new water coming out of the spigot to run into the water that's already there, and your hose starts producing water, or the far end of your hose starts producing water a lot earlier. So our current carrying wire is just like that hose that's already filled with water. So instead of waiting for a single electron to go all the way through these 20 centimeters or for a single drop of water to go all the way through your hose, all you really need to do is institute some sort of change that will cause momentum to transfer from one drop of water to the one directly in front of it, or from one charge carrier to the particle directly in front of it. So if we know what this material is made up from, so we can look at one of our electron densities, or I don't think they give us any indication of, oh no, we do know. So this is copper wire. So we can look up the electron density from the table that we saw earlier. We know how many available mobile electrons there are. So we can estimate how far any one electron would have to travel before it bumped into its nearest neighbor. And that distance is very, very small. So the chain reaction that is the result of one particle bumping into its neighbor, the next one bumping into its neighbor, and so on, results in a really small amount of time. And I don't have a value here. I don't think it's indicated in the image, but this is usually on the order of nanoseconds. So something that is small enough that to us, if we don't have any other device to use to measure this, to us, it seems like it's happening instantaneously. And it's not exactly instantaneous, but it is nowhere near the half an hour that you would have to wait if you were relying on a single electron to make its way from one plate to the next. So we know that the charges that start off in that wire have to receive a force from somewhere in order for them to accelerate, because otherwise they are in an electrostatic scenario, just like the charges that are on the plates of the capacitor. So they've spaced themselves out as best they can, but once they have figured out what that spacing is, they are fixed in location. This is also similar to the chargeable rods that we used a few weeks back in the electrostatics lab. We noticed that when we charged up, let's say, the rubber rod with the fur, we weren't constantly discharging that rod just by virtue of touching it with our hands, because the rods were made up of insulating materials. So when you did some work on them, you could get a negative charge to go from your, like the fur to the rod, the rubber rod. Or if you were using the other pair, you can get an electron to go from the glass rod to the silk so that you end up with a charge imbalance. But you literally needed to do mechanical work in order to achieve that. So there has to be some mechanical component that we can ultimately credit with, or that we can seek out as the reason why these charge carriers start to move, why they don't just stay at rest the entire time. So we can relate this back to a simple semester 1 type example. If you are trying to push an object across a surface that's rough, but you don't want this object to continuously accelerate, you just want it to go from being at rest to moving with some constant velocity. All you would need to do is first exert a force on the object that's enough to get it to overcome static friction. But once that's happened, you can ease up a little bit and only exert enough force to overcome kinetic friction. And this image here only shows us how the book is behaving after it started to move. But if we had another free body diagram that showed the book as you were pushing it with your hand, so when you were trying to kind of evaluate how much force it would take to get the book to start moving, the static friction, or the maximum static friction vector that the book could experience before it started to, or I guess the maximum static friction force that the book would experience before it started to move, it would definitely be larger in magnitude than this FK value is. And that's because the coefficient of kinetic friction for any two surfaces is always a little less than the coefficient of static friction. So once it started to move, all you really have to do is make up, or to exert a force on this book that's just enough to overcome FK. So the net horizontal force in this case is going to be 0, but the book is actually moving. So it would be a case of dynamic equilibrium as opposed to static equilibrium. And if we replace the book with the charge carriers that are in the wire, recognizing that the actual charge carriers are negative, so the force of the push is not coming from your hand, but from an electric field. And we know that the force vector and the field vector have to be anti-parallel for negative charges. I guess the reason why charges go from being stationary to now moving in the direction of F push, it's got to be something that we can link back to the internal electric field in this wire. And up until this point, we really have not cared about the electric field on the inside of a conductor. We only thought about the electric field produced by some conductor. So specifically, if you think about that problem near the end of the electrostatics lab, where we imagined polarizing a couple of metal spheres, touching them to one another, and then separating them so that they ended up with some charge imbalance. One would be positive, one would be negative. So the force that actually caused a charge to go from one surface, or an electron to go from the surface of ball A to ball B, for example, that had to come from the electric field produced by that external charge. Here, there has to be some sort of non-uniform charge distribution on the outside of this wire in order for this electric field to be non-zero. So to phrase that another way, if we relate the wire to the plates of the capacitor that we talked about earlier, we know that when the capacitor's plates are not connected with a wire, the charges on their surfaces don't move. But as soon as they are connected with the wire, these charges can get even further away from their nearest neighbors, and they take the opportunity to do that. Here, if you have charges that are arranged unevenly on the outside of a wire, an internal electric field will arise. It will go from 0 to non-zero. And that electric field is ultimately what's responsible for pushing these negative values toward, or these negative charges toward the right. So there's a frictional force here that's not quite as straightforward as the kinetic friction force that we can imagine acting on this book. But instead, imagine that you are trying to, let's say, move an object through a wind tunnel, let's say. And if you know, let's say, the cross-sectional area of that object, if you know the coefficient of drag, you can quantify the amount of drag that object feels. We're doing something similar. We're thinking about this in a similar way here. So instead of tracking a single electron as it goes from one end of the wire to the next, think about all of the elastic collisions that this electron will undergo with other charge carriers and with the positive charges that make up the lattice of the interior of the wire. So there will be some resistance to the force that the electric field is exerting on our negative charges. And that resistance is going to have to be oriented opposite the direction of V. So I have two force vectors that have the same magnitude. So specifically, this snapshot of our electric field on the inside of this wire can only pertain to a case where there was a non-uniform charge distribution on the outside of the wire. So our charge carriers are not stationary. They've already been sped up, but they are moving with some constant velocity at this point. So this scenario here is one that we saw, I think, for the first time at like the halfway point of our electric potential chapter. We imagined that we had a battery that was connected to two segments of wire, but there was a gap on the far side. So if we were to take a voltmeter and measure the potential difference between the terminals of the battery, we would get the same value if we touched the voltmeter probes to the ends or to either side of this gap. And we rationalized that by recognizing that the wire segments were going to give the charges that were already internal to the battery even more space so that they could spread themselves out. But they will eventually stop moving. Once they figure out what that optimal spacing is, then they don't move anymore. You have an electrostatic situation. So we said that the delta V between the gap in the wire would be exactly the same as the delta V between the terminals of the battery. Another way to think about this is to imagine that the imaginary escalator switches off after these charges get as far away from one another as they can get. So instead of the battery, if we have a charged capacitor, but we still keep this gap in the wire, these negative charges are going to spread themselves out as best they can. We have an electron deficit that is representing these positive charges that are, again, spaced out as well as they can, but they're going to stop moving. So this is another electrostatic scenario. If we could look at the internal electric field for the wire in this scenario, we would come to exactly the same conclusion that we did when we were talking about the charge on the inside of a conductor, like back in chapter 22, 23 in that area. So the electric field on the inside of that conductor was 0 in that scenario. That's also true here. But if we consider what happens when we join these two pieces of wire together, current is going to start to move because now a negative charge can get even farther away from its nearest neighbor. And I can say the same thing for the positives. So until there is some sort of connection here, these charges are not just going to be capable of jumping across the gap. Oh, excuse me, faster than I wanted. So let's imagine that this snapshot pertains to the point in time right after you've connected the two ends of the wire. So the capacitor is in the process of discharging itself, but it's not done yet. What we would find here is that the space or the section of the wire that's furthest away from the capacitor is going to be the part that has the smaller surface charge density, because each one of these charges is still kind of in the process of moving or making its way around this loop. And if we think that if we imagine our negative charges moving counterclockwise and our positive charges spreading themselves out clockwise, eventually the opposite plate of the capacitor is going to become neutral. And I guess when I say opposite plate of the capacitor, I'm imagining that we're starting by thinking about the negative plate and then figuring out what will happen to the positive plate. As a whole, this entire capacitor and wire system is still neutral, but these particles they're in the process of moving here. So after something on the order of nanoseconds, they will spread themselves out evenly. But while that spreading is happening, the electric field on the inside of the wire is non-zero. So we could either connect an ammeter to this circuit to track the amount of current that's moving through this wire loop as a function of time, or we can look for the other indicators that we talked about earlier. We can maybe detect a change in the temperature of the wire. That's something that is purposefully difficult to do with wires that are surrounded by cladding. But if we imagine that we just had a bare copper wire, we would be able to feel it warm up a little bit as a result of the charges on the interior of the wire working against that frictional force that's present on the interior. And if we had a compass needle, we would see it deflect in this scenario here. But again, this is not something that will actually go on forever. This capacitor will eventually completely discharge, so that, again, the negative charges have spaced themselves out, but they've found the optimal spacing where they don't want to be any closer to their nearest neighbor than they absolutely have to. And then when that happens, the current in the wire goes to 0. So that also has to mean that the electric field on the inside of the wire gradually goes to 0 as well. And at first thought, it might not be obvious how that happens or how the electric field kind of switches itself on or off. But this is something that we can relate completely to the charge distribution on the outside of the wire. It's non-uniform here. I've got really small magnitudes of charge far away from the plates, relatively large magnitudes close to the plates. When that scenario kind of neutralizes or resolves itself, the field switches off, which means that the current goes to 0, which means that the charges are stationary. So this diagram here, I just want to blink back 1 second because it is oriented the opposite of the capacitor that we were working with here, where our the left segment of this little wire portion on the bottom starts off more negative than the positive segment. Imagine that we could just take that capacitor and flip it like this. so that now I start off with this section of the wire on the left initially being closer to the positively charged plate of the capacitor, and the wire segment that's on the right is initially closer to the negative plate. So if this image here represents the interval or a snapshot in time right after you connect the wire so that the capacitor can start to discharge itself, I'm going to find that the surface charge density is going to be different magnitudes and different signs depending on where I chose to look. So we're imagining that we can take just a slice of this wire and only consider the charge that's on the outside, because that's ultimately what's responsible for producing an electric field on the inside. I've got one slice here where I imagine that surface area is exactly the same in all four cases. I've got a net charge of +5 on slice A, a net charge of -5 on slice D, and then a ±2 on slices B and C. So these charges are not arranged in a uniform fashion. That means that there exists an electric field in the interior of this wire. And if we think about the slices of wire as being similar to these discrete point charges that we started working with in like chapter 23, when we were working out those system of point charge problems, we know that the electric field in the space between slices is going to have to be the sum of the electric fields produced by each individual slice. So to say that another way, imagine that we're placing a probe charge in between slice A and B, and we're measuring the electric field that, or I guess really the electric force that those slices would exert on the probe charge. No matter what the sign of the probe charge is, and if we assume it's a positive just to keep things simple, the electric field vectors that are being produced by slice B will have to have the opposite direction of the ones that are being produced by slice A. So the net field in this section is going to be oriented toward the right, but it's going to have a magnitude that is equal to the magnitude of EA minus the magnitude of EB. We're just figuring out what the net field vector magnitude would be exactly the same way we would if we were talking about forces that were acting on an object. And if we look at the space between slices C and D, we see a similar thing happening. Now I've got a field produced, or like a surface charge density for slice D that's going to produce an electric field vector that's stronger than the one that's being produced by slice C. But they have to disagree with each other because I have two negatives for the case of C and D, two positives for the case of A and B. So the net field is still going to be oriented toward the right. And if we look at the section between slices B and C, now I have field vectors that agree with each other in direction, kind of similar to the way that field vectors agree with each other in the space between plates of a capacitor. So I know EB and EC are going to add together now so that the field vector in that space is going to be a larger magnitude than either B or C alone. What we end up with here is a net electric field that has the same magnitude for all points inside of the wire. So that means that once your charge carriers start to move, you're not going to find like one electron that accelerates while another one is moving at a constant speed, or one that decelerates while another one is accelerating. They're all going to receive the same force. Thus, the field strength is going to be the same in all regions of this wire. Now, it gets interesting again when we consider what happens when the capacitor is close to being completely discharged. This net electric field vector is going to shrink in magnitude until it becomes 0. And once it's 0, it's no longer going to be capable of producing a force that can act on the charge carriers. So your charge carriers will go to rest, just as if you stopped pushing the book that we saw a few slides earlier and just gave the maybe gave the book a quick jolt. Eventually the book would slow to a stop, and the charge carriers are going to do something really similar when that electric field goes to 0. So the direction of the net electric field vector is going to be consistent for all points inside of this wire. And if we were to kind of flip this back to the orientation that we saw in the previous slide, the only thing that we would change is the direction of E net. The magnitude would stay the same. So it's that net field that is ultimately responsible for the force that causes charges to move from left to right, as we saw in our previous example. So let's imagine that we've got a new wire with a new surface charge distribution as shown here. So the left end of this wire segment is more positive than the right end. I've got a larger magnitude of positive charges on the left, a smaller magnitude on the right. The electrons in this wire are going to be constrained to move along the same axis that the wire has. So in other words, we can eliminate C and D right off the bat. These charge carriers are not going to move from the bottom of the wire to the top or vice versa, but it's going to be either left to right or right to left. We can also get rid of E because if the charge distribution or the surface charge distribution was uniform, then these charge carriers, the electrons, would stay at rest. And what is a little bit tricky about, or what's a little distinct, I guess, about choice E is that if we're considering the individual charge carriers relative to all the other charge carriers that exist inside of this wire segment, I guess I would need to be able to describe the motion of any one electron relative to any other electron that exists inside the wire. But still, even if all the electrons are moving in the same direction, if they are on average at rest with respect to one another, that doesn't negate the fact that the sea of electrons is shifting as a whole. So there will be a current on the inside of this wire. The last thing that we need to pay attention to is the charge carrier. So we're not looking at conventional current, we're looking at the legitimate charge carriers, the negatives. So if our field vectors have a magnitude that's going to be oriented toward the left side of our screen, we know that the charge carriers are going to, I think I said that backward. The electric field vectors, so the left end of the wire is the one that's going to be more positive. The right end is going to be less positive. So if we think back to what our wire slices look like here, our net field is going to point away from the more positive side toward the more negative side. So that means that our field vectors are going to be oriented toward the right. The charge carriers are electrons, so the force acting on them is going to be opposite. So the drift is going to be oriented toward the left here. Okay, so this part of our conversation actually harkens back to, I think like near the end of the first half of chapter 22. That's my dog sleep barking. Okay, so anyway, this harkens back to a conversation that we had around near the end of the first half of chapter 22, when we were talking about how conductors can be polarized. And we recognized that conductors were distinct from insulators because the conductors did have a bunch of valence electrons that could freely move around through the interior of this material. Insulators were the opposite. You could influence the orientation of the atoms in that material, but you were never really separating the electrons from the positively charged nuclei. This kind of highlights why, if you were asked to design a circuit, it would be a really bad idea to make wire out of something that insulated as opposed to choosing something that was a natural conductor, because you want the sea of electrons to be plentiful and easy to move. So you've chosen something that's a conductor. If we kind of shift our perspective away from the sea of electrons and imagine looking at a single negative charge carrier as it interacts with the particles on the interior of this conductor. When there is no interior electric field, this electron is going to interact with these positively charged nuclei the same way that you might imagine a pinball interacting with the elements inside of a pinball machine. So like not the spring that you would use to launch and not like the little paddles, But if you think about how that ball just interacts with all the stuff that is fixed in place, that's not too far off from what would happen to the electron if there is no electric field on the interior of this conductor. But if this conductor is a wire segment, and that wire segment is carrying current, we know that there is going to be an internal electric field inside of that wire segment or that conducting material. So we can think about what is different about the behavior of this electron when E is not equal to 0, compared to this case here where E is equal to 0. So if we imagine this one electron goes through the trajectory that's shown here, if I wanted to calculate the average velocity of this electron, not the average speed, but the average velocity, I would get something that's essentially 0. Because for every trajectory that's oriented in the positive x direction, or kind of into the first quadrant, sort of like this first interaction here, where it kind of points up and to the right. For every one of those, there's nothing precluding me from being able to find another trajectory that is anti-parallel to it. So in other words, there's no overarching trend between the direction that this electron is going to drift. It is sometimes going to be drifting toward the left, other times toward the right, sometimes up, sometimes down. So the average velocity there would be around 0. So this single electron here is not making its way from the left edge of this conductor to the right edge. It's always just kind of, it's experiencing essentially a 0 net displacement because of the fact that it is equally likely to trend leftward as rightward. This changes when there is an electric field on the interior of this conductor. So the straight line trajectories that we have here are now going to be bent into parabolas because there is another force, the force that's acting on these electrons is not, or let me phrase it this way, the only time this electron is experiencing a force is when it's undergoing a collision with one of the positively charged nuclei. But that's not the case for the non-zero electric field scenario. So there's a force that comes from the field itself that's acting on these particles that we can combine with the force that the particle feels when it's undergoing a collision with a positively charged nucleus. So we have something that is, or we have trajectories that are closer to what we saw when we discussed projectile motion in semester 1, where this path is not just a straight line, not something that we can collapse into one dimension, but something that at best we can collapse into a plane. So here I have a negative charge that is being influenced by the internal electric field. So it does eventually undergo a collision with its nearest positive, but these trajectories not being straight lines anymore means that there is an essentially a downhill direction, or there is an influence or trend to the velocities that I would expect to find here. So the trend here is that the electron would kind of tend toward the right because of the orientation of the electric field being opposite and our charge carriers being a negative. So like left to right is like downhill for the interior of this trajectory. So if I did let this particle undergo some collisions over some interval delta t, I would find that my net horizontal displacement isn't a 0 anymore. And it would be something that I can indicate with a displacement vector that would point toward the right. So the presence of this electric field on the interior of the conductor is what kind of keeps me from having an average velocity equal to 0, which is the case when there's no electric field on the interior. So that's not all that different from what we saw when we were considering slices of a wire and trying to make sense out of the direction that a negative charge carrier would start to move once it was accelerated from rest. Now, if we think about, from an energy perspective here, this scenario where there's an additional force acting on this particle as it's going between collisions, this would be not dissimilar from the force that your palms exert on one another when you rub them against one another. So what I'm specifically talking about is the amount of work that that frictional force between my palms will do. So the frictional force from like my left palm and my right palm will do work that causes the opposite hand to warm up. And this is kind of like the reasoning and the rationale for that indicator where you can, if there's no, or if there's insufficient cladding on your wire, you can actually detect that the temperature is a little bit higher when current's moving through that wire compared to when it isn't. This is just an energy argument that we can make. So now that there is a non-zero average velocity for our conductor that does have an internal electric field, there is an additional thing influencing how long you would need to wait in order for your electron to undergo, let's say, like 2 consecutive collisions. So to go back to this image here, if we were to choose like this first collision between our electron and our positive ion, that's our positive nucleus here, and then if I purposely looked for a collision that involved a greater or like a longer trajectory, I can surmise that the amount of time that it would take for this collision to take place is going to be a bit shorter than it would take for this collision to take place. Because the electric field being consistent means that the force is not getting like stronger or weaker. It's just, I guess there's a net force acting on the electron as opposed to just one force coming from these collisions. So if the net or the average velocity is not zero anymore, you will have to wait different amounts of time before you would expect your electron to go through 2 consecutive collisions. And that's what this graph here is kind of illustrating. Imagine that forward or like toward the right is a positive velocity, toward the left is a negative velocity. I can find a bunch of instances here where my particle is in the process of speeding up toward the right because that is the downward that's the downhill direction for this particular conductor. But when it undergoes collisions, the velocity will go from not a non-zero positive to 0 when the object is, or when the electron is at rest. But then if we're thinking about these collisions as being similar to the elastic ones that we talked about in semester 1, then we know that when that electron rebounds, it should be going the opposite direction. So I have a velocity here that starts off positive and becomes more positive when the electron is accelerating toward the right. There's a quick change in velocity here that matches up with the collision itself. And these are kind of indicated as these vertical dotted lines, or they're almost like asymptotes. We're imagining that these collisions take place they take place almost instantaneously. So I have my particle that's moving toward the right and speeding up. It goes through this collision. Now I have something that's moving toward the left and slowing down. It's going to now switch direction and move toward the right while speeding up again because the slope of this segment is consistent. That's something that would depend on the strength of the force that's acting on these charge carriers, which itself is something that we can indicate with the magnitude of the electric field that is on the interior of this conductor. But the point here is that I can't count on a pair of consecutive collisions being separated by the same amount of time. I know that I wouldn't expect to wait a very long amount of time for a particle to undergo 2 consecutive collisions, but I might get lucky and end up with 2 collisions that are spaced really close together in time compared to 2 that are spaced a little bit further apart in time. So it wouldn't really be helpful to evaluate a single delta t, so the amount of time between collisions. I need to kind of back up and evaluate the mean time between collisions. And that is the meaning of tau here. So unfortunately, we're going to run into a handful of different taus in this unit. This tau is just the mean time between electron collisions. It will never show up in a problem that's also asking us to evaluate the torque on an electric dipole or something like this. So until we get to our discussion of magnetic dipoles and how they can respond to a torque from some external field. Anytime you see a tau, it's going to be referencing a time. So it's useful to know how to relate that time to the delta T that we included as part of our definition of electron current a little bit earlier. But before I jump the gun there, if we think about the force that is going to be acting on this charge carrier between collisions, the force is going to come only from the electric field. There's no other agent that's acting on our charge carriers. So that means that the horizontal acceleration is predictable. And if we know the magnitude of the force that is coming from the field, which is just the charge times the electric field strength, I end up with something that is familiar. We saw a similar expression when we were talking about the behavior of a particle, in a charged particle inside of a capacitor. We were able to surmise that that scenario was pretty similar to projectile motion because the field vectors meant that there was only, or that the forces that were acting on that particle only acted in one direction. So they were only vertical, not horizontal, sort of like a projectile. So the acceleration was this charge to mass ratio, E over M, times the electric field strength, E, capital E. Now I can incorporate I can kind of get rid of the acceleration here and express it as some combination of the average drift speed and the mean time between collisions. And I end up with a speed that I can express in terms of this product. So a charge in coulombs times a time in seconds divided by a mass in kilograms. If you multiply that by the electric field unit, so Newton per coulomb would be the smart choice here, as opposed to volts per meter, even though they're identical. It's easier to see how the kilogram cancels out and what happens to the coulombs that are native to the Newton per coulomb. So anyway, if you look at the units here, you're going to end up with 1 meter that was a part of the Newton, that is a part of the electric field unit. You're left with 1 second. It's going to be one of the seconds that's in the denominator of the Newton. That's a part of your electric field unit. And I have meters per second. That's all that survives. So if I have a way to, let's say, measure the electric field on the interior of our wire segment, which is something that we can do, if I know the charge to mass ratio for the electron, which is something that we can measure directly, and we will do that a few labs in our future, all I would really need to know is the mean time between collisions to get an estimate for the drift speed. And this logic is where that 10 to the minus 4 meters per second estimate that we saw earlier comes from. This is how we can actually back that up or justify that allowing for different electron densities, if subjected to the same electric field strength, then no matter whether you choose by choosing a copper wire, or if you were to choose like a gold wire or something that contributes a smaller number of electrons, no matter what, the drift speeds would all be about on the same order of magnitude. Now we know how to relate drift speed back to the electron current. All we really need to evaluate is how far the sea of electrons would shift over some time interval delta t. And believe it or not, here we can look at how these units cancel each other out or how they relate to one another. Our electron density is like a number of particles per cubic meter. We have our charge to mass ratio, E over M, so that's coulombs per kilogram. Tau is measured in time, and this cross-sectional area, of course, is going to be meters squared. When you multiply that by electric field units, everything except for 1 second is going to cancel out. I'm going to have a second in the denominator so that I can interpret that electron current as the number of electrons per unit time that pass through a certain part of a circuit. And here, if we think about imagining that you've got, let's say, a segment of wire, it's got a fixed length, a fixed cross-sectional area. It's made of just one material, so there is a fixed constant electron density. If I were to assume or like connect that wire segment to, let's say, a 6-volt battery and then a 9-volt battery, it would make sense that the currents in those wire segments should be different, because it's almost as if the imaginary escalator inside of those two batteries have different heights and they are set to different speeds. So in other words, they don't give the particle the same, they don't give the charge carrier the same amount of potential energy, but different amounts of potential energy. So if that's the case, then the field strength on the interior of those wire segments should also change based on the voltage of the battery that we're imagining using to set up this circuit. So everything but the E here, everything but the capital E, the electric field strength, everything but that is a constant. So the stronger the field, the faster your imaginary escalator is traveling. So the greater the number of particles you can feed through a certain section of your circuit per unit time. Everything else there can be assumed to be a constant. All right, that's the end of the first half of this chapter, but we've still got like around a half hour. So I'm going to switch to part 2. But while I'm doing that, do you have questions or concerns, anything that you want to see or hear one more time before we go to the second half?
I actually had a very quick question about the drift speed.
Yes.
So is VD a constant? Like, is it always going to be that 4 times 10 to the negative 4th power?
If we are concerning ourselves not with the interval of time where the electrons are going from rest to whatever V sub D is, or when they are going from VD to rest, then it is safe to assume that that velocity is essentially constant. And that's relative to all the other electrons in the circuit.
Okay, so we should always assume it's going to be that number unless it's specified as something else?
Yeah, if you are given like enough specific information about the cross-sectional area of the wire, what it's made out of, all of that, then you can calculate a more like specific or more accurate drift speed. Okay. But for the metals that make good wires that conduct well, they're all kind of in that same neighborhood. And it's safe to use that estimate if you don't have specific information about the composition and all of that.
Okay, thank you.
Sure. Okay, so let me, so this one here, I'm gonna reshare, get to part 2. So now we should all be able to see current and resistance part 2. So here is where we kind of directly confront the difference between electron current, which is what's legitimately happening to the charge carriers in a circuit, and conventional current, which is a way for us to consider the motion, or I guess not like the hypothetical motion of a positive charge, even though in reality we know the positive charges are not going anywhere. So the way that we can distinguish between electron current and conventional current is just by looking at the case of the I that we use to indicate it. So lowercase I is always going to be an electron current. Capital I is always going to be a conventional current. And we can think of this as not just the rate of change of like the rate at which our imaginary positive charge carriers move past a certain point in a circuit, but instead we can think about this as the first derivative of charge as a function of time, where we're imagining that our circuit is connected. So imagine we have a battery and let's say a capacitor or something that we're trying to charge up. for all the time that it takes for the capacitor to charge, the imaginary escalator is going to be on. It's going to be giving potential energy to our charge carriers so that they can move through the circuit and then get reloaded again once they make it to the bottom of the escalator. If we were to let a lamp, let's say, stay on for a minute or so, we could determine exactly how many electrons moved through a certain part of the circuit in that minute. And we could compare that to the total amount of charge that had to have moved past that same point. So think of capital Q as some macroscopic amount of charge that is made up of a bunch of individual charge carriers all having the same fundamental charge that just go past or maybe go into an ammeter per unit time or go past a certain point in the circuit per unit time. So we can define our conventional current as the first derivative of that charge with respect to time. And if we're talking about just a traditional circuit that involves a, let's say a battery and some wire and some resistance element, that resistance element can be a light bulb for just for like the simplest way to visualize how this resistance is working. So if it's a light bulb, we have it connected to a battery with a couple of wire segments, then the amount of charge that it takes to keep the light bulb lit for 1 minute is going to be more than it takes to keep the light bulb lit for 30 seconds or for just a single second. So if we know that our escalator is pushing at a consistent rate, which is a safe assumption for a traditional resistor, then we know that this current capital I is something that I can just express as some constant number of coulombs per second. And that is the source of the amp, the SI unit for current. We encountered this if you had a Tuesday lab. We measured the current in a circuit directly with a DMM, kind of similar to the way that we measured delta V in our equipotential surface lab. I want to just point out here that I tend to write out amp when we're solving a problem or something like that, because we are going to find ourselves in situations where both the cross-sectional area of a wire segment and the quantity of current moving through it are both relevant. So whenever you see a capital A, that is a unit, it's referring to the amp, but we will also encounter capital A's in equations that refer to the cross-sectional area of something. So let's imagine that we can take an interior view of what's happening to our discharging capacitor here. So I start off with a bunch of, or with some surface charge density shown here. All of my positive charges are on the right, negative charges are on the left. Once I connect these two plates of the capacitor, I know that the negative charges are going to start working their way through this loop counterclockwise, so that the magnitude of the charge on the opposite plate goes from being a large positive eventually to having zero net charge, so an equal number of positives and negatives. I can imagine that these negative charges moving counterclockwise behave exactly the same way that a positive charge would if it were moving clockwise through this loop. So if we imagine that positive charges are the ones doing the moving, then the direction of the electric field vector and the force acting on that positive charge carrier, they are parallel to one another as opposed to anti-parallel, which is the case for the negative charge carrier. So imagining or treating the positives as if they're the ones that are moving, that kind of saves us from potentially making a directional error. So missing a negative sign that would let us perhaps inaccurately determine the, let's say, the magnitude of current in a more complex circuit, something that has like maybe 2 light bulbs or more than one resistance element. So here I'm mostly going to talk about, if I just refer to current without any sort of qualifier, take that to mean conventional current. So the rate is going to be exactly the same, but conventional current is going to drift from right to left. The electron current would drift from left to right. So if instead of, let's say, instead of measuring the amount of charge that goes through, let's say, a light bulb that's connected in circuit every minute, let's say, instead of evaluating the amount of charge that goes through that light bulb every minute, instead what I could do is use an ammeter to evaluate the rate at which charge moves through that ammeter. So it's about, and I guess in the way that an ammeter actually works, you are weighting a very small delta T in order to get a readout of what the current is. But that delta T is going to be really small compared to the amount of time that the light bulb remains switched on. So we can think of that definition of the current being dq dt as something that we can also express as our total current Q divided by the amount of time that that current is passing through some part of your circuit. If we are treating our positive charges as if they are the actual charge carriers, then the quantity of charge here is going to be equal to the fundamental charge of the proton, which is exactly as large as the fundamental charge of the electron, only positive instead of negative. If we know how much charge we're attributing to our hypothetical positive charge carriers, and we know the number of electrons that are legitimately moving, then the product of those divided by T should give us a relationship between the fundamental charge and the electron current. So another way to think about this is to imagine that you set up a circuit, you measure a current, and let's say that that current is 2 amps. You know how to take that current and break it down into the number of individual electrons that have to be moving in a certain direction with a certain speed in order to make up that current. It's almost the same as, or it's similar to, and the way that I tend to think about it when presented with a problem that asks me to think about the number of charge carriers that it takes to make up some conventional current. I can take this current that's measured in coulombs per second and figure out how many electrons it takes to make up that same number of coulombs. So you're sort of thinking, or I tend to sort of think about it as a dimensional analysis type thing. If every charge carrier contributes the same amount of coulombs, and I know that my lamp that's been on for 1 minute, let's say, requires a certain amount of charge, capital Q, to stay lit, all I have to do is take that charge, divide it by the number of electrons that produce that charge, and I know the number of imaginary positive charge carriers that would have to pass through that circuit segment in an amount of time. One thing to gloss over here, the electron current is something that we can measure just in terms of electrons per second. So when I multiply that by the fundamental charge, now I have coulombs per second on the right, coulombs per second on the left. So let's imagine we have a section of wire that moves or that channels or facilitates the flow of 120 coulombs of charge every minute. We wanted to calculate the current in this wire. All I would need to do is take this quantity of charge, divide it by the delta T. And since all of our current units here are in amps, I would need to take that delta T and convert it from minutes to seconds. So 120 coulombs divided by 60 seconds, that's how we get 2 amps. Now this here, if you had lab on Tuesday, you've already kind of gotten a little bit of a taste of how current density works. We know that current density is the ratio of current to a cross-sectional area, but from the way that we defined electron current in the first half of this chapter, and the way that we just defined, or the relationship between electron current and conventional current on the previous slide, we can express this current density J in a handful of different ways. The units are all going to boil down to amps per meter squared, but we can get there by taking the number of particles per cubic meter multiplied by the number of charge per particle multiplied by a time. I'm going to get an amp, so like a coulomb per second is going to show up from the fundamental charge E and the second that is in the denominator of the velocity unit. And then I'm going to have a meter squared that's going to be the result of multiplying the meter that is in the numerator of the velocity unit by the 1 over cubic meters that is in the unit of electron density. So I've got a current and an area that stick around. So for question 2, we have this kind of squared off wire segment just so that it's easier for us to evaluate the cross-sectional area. So instead of having to calculate pi times some radius, we can assume that this cross-sectional area is just going to be 4 millimeters cubed. So I want to remind us, this is something that we needed to consider it when we were talking about thermodynamics in Unit 4. So the way to convert between like cubic meters and cubic centimeters, I can't just move my decimal point 2 places in either direction, because even though a centimeter and a meter are different by 2 decimal places, if you are evaluating an area, you need to take those 2 decimal places and square them. If you're evaluating a volume, you need to take those 2 decimal places and then cube them. So you have a this cross-sectional area would be 4 times 10 to the minus 6 square meters. So you could also achieve exactly the same thing by just converting that length and height to meters to start off with. So I get 4 times 10 to the minus 6 cubic meters. If the current in this wire is 8 amps, this ratio is going to yield 2 times 10 to the positive 6 amps per square meter. So an 8 amp current is fairly large. I mean, it is a lot smaller than the ones that we will or may have already measured in our conductivity lab that we're doing this week. So let me pop this chat back out because I lost it. Looks like we're still okay there. Jump in at any time if you have questions about anything. Here we want to revisit a conservation law that we touched on in the I think the potential chapter, when we were first introduced to Kirchhoff's loop rule. We imagined that if we had some space that was affected by some either source charge or group of source charges, if we moved a probe charge in any path that we wanted, as long as it was a closed loop, we knew that the total delta V was equal to 0. Kind of similar to the way that if you were, let's say you drive to campus, you get a parking spot, you get out, you go to all the classes that you have on campus, and then you come back to your car after you're done. Your displacement over the course of your entire day or your stay on main campus would be 0 meters, even though you may have walked a very large distance. You may have gone to 3 or 4 classes as opposed to just staying in your car all day. So the law of conservation of current is something that we can relate to Kirchhoff's loop law in this fashion. So imagine you have a charged capacitor. It's connected to a simple circuit that involves 2 small flashlight batteries or flashlight light bulbs, A and B. They're identical to one another, so they have identical brightness here. If I traced a single negative charge from the negatively charged plate, there's no opportunity for it to divert. There are no junctions anywhere in this loop. So it is constrained to go through this wire segment, through bulb A, through the next segment to bulb B, and then through the last one to get back to the positively charged plate. So there are no other options. There's no place that this current can split up. So the rate at which electrons leave the negatively charged plate, that's got to be the same as the rate at which electrons go into bulb A. That's got to be the same as the rate at which electrons go out of bulb A and into bulb B. And I can say something similar for the rate at which they leave bulb B and start to accumulate on the positively charged plate. So the amount of charge I put in is going to be exactly the same as the amount of charge that I get out on the other side. So in this case here, we're meant to assume that these bulbs are identical. This would be true even if I had like a tiny flashlight battery and a 100-watt light bulb. as long as there are no junctions, the amount of charge that goes into one bulb is going to be exactly the same as the amount that goes into the other. So if we think about this in terms of subdividing a current carrying wire, if I could take, let's say, this segment of wire and imagine that this is a part of a complete circuit that I can disassemble. And I can split this section of wire and put an ammeter in between there to complete the circuit. I would measure the same current going into this wire segment as I would moving out of the wire segment, and as I would if I subdivided this wire and put the ammeter in between these two wire segments. As long as there's no junction, then there's no place for current to move or to split up or rejoin. So that means that the amount of current going into this section of the wire is exactly the same as what's coming out per unit time. It's exactly the same as what's traveling through the interior per unit time. So now imagine that we've got two light bulbs that are attached to a battery as opposed to a charged capacitor. They're identical to start with. We want to evaluate which one is brighter. We would find that they should be equally bright because the same amount of charge is going through each of these identical light bulbs per unit time. So the current in bulb A couldn't possibly be different than the current in bulb B. And those are both equal to the current that the battery is producing. So imagine the imaginary escalator that's moving a charge from the bottom terminal, the negative to the positive terminal. Depending on the speed of the imaginary escalator, it can push charge really quickly or more slowly. And for increasingly complex circuits, we can imagine that the speed of our imaginary escalator is variable as opposed to being the same all the time. So the battery is not always going to work it's not always going to work at a constant rate. It's something that will, like the amount of current will scale based on the job that the battery is actually trying to do. So if instead of these two light bulbs that I have in series, if I had 100 light bulbs in series, then the rate at which current moves through any one of those light bulbs would be smaller than what we see for this case here. So, and like a consequence of the law of conservation of current is now the second of our two circuit laws that we can attribute to Kirchhoff. So in addition to Kirchhoff's loop law, we have the junction law here that just states that if one wire splices into two or two wires are joined up into one, the amount of current that goes into that junction can't be different than the amount that comes out. So I can sum up all these input currents and then set them equal to all of the output currents. So this thought question gives us an opportunity to think through this scenario. We have a 4-wire junction where I know the direction and the magnitude of current for 3 out of the 4 wires, and I want to figure out the current in the 4th wire. We can eliminate not enough information to tell because this is something that we can answer. I know that I have 2 amps coming in from the left, 5 amps coming in from above, 9 amps exiting from the junction. So I can account for 7 amps going in. I know that there are 9 amps coming out. So my unknown wire has got to carry 2 amps. And it's got to carry 2 amps into this junction. Otherwise, there's no way to account for the presence of 9 amps exiting as opposed to just 7 amps if there was like no current in this wire segment. So 2 amps into the junction or 2 amps toward the left for this specific setup. Now the current density in a segment of wire, we're going to imagine that we are not, I don't know why I'm getting a bunch, well, I guess a lot of people are sending emails right now, so I have like a bunch of little notifications to dismiss. But if we imagine that we're looking at a single wire segment, so not something that splits into junctions, I know that the amount of current, or like the rate of current, the rate of charge flow on the interior of the wire is something that I can attribute to the force that the electric field is providing on the charge carriers on the interior. So that same current density that I can express in amps per square meter, I can also express that as the product of this conductivity sigma, which is a constant, just like the specific heat or the electron density. It varies with material. And the electric field strength E, you can imagine that that is something that we can equate to the speed at which your imaginary escalator inside the battery is moving. So the product of these two should get me back to amps per square meter in some way. And I know that I can express an electric field as either newtons per coulomb or volts per meter. So the units of sigma, the conductivity, have to be something that kind of squares that circle, that gets me from something involving volts per meter times some constant quantity into amps per square meter. Sorry. Okay, so this sigma here is something that we can measure directly, which was what we did we are doing in this week's lab. It's also something that we could calculate, provided we know the physical properties of the material that makes up the wire. So the electron density, the mean time between collisions, and then I have this charge to mass ratio where there's an extra unit of E, an extra fundamental charge up here at the top. So it's not immediately obvious at all how to make sense out of those units, but to jump forward here, just so that we can, oh no, okay. I thought it was a bit later than it actually is. So let's go back to our normal pace. So if we can look up an electron density, we have Coulomb squared that we can attribute to the E squared here. Tau, the mean time between collisions, is just a time, and then this M is going to be a kilogram. So we're going to end up with some combination of volts, amps, and meters. Now, conductivity, if we think about when we first started to talk about insulators versus conductors, we knew that a material that was a poor insulator was a good conductor, and then vice versa. Conductivity and resistivity they describe a similar relationship. Something that conducts well resists poorly, and something that resists well conducts poorly. So this sigma can also be, or I can take the reciprocal of sigma and use it to express the resistivity of a material. And I want to give you a heads up here. It is not going to be impossible that we would encounter a problem that involves the resistivity of a specific material and the density, the mass density of that material, rho. So look for context clues so that you can tell whether the rho that you might be given in a homework problem or an exam problem, whether that refers to a mass density or a resistivity. So this last chain of thought questions will kind of give us an opportunity to think through how current density, and like electric field relate to one another. We're imagining that we've got two wire segments that are welded together. They're made of the same metal, but there is no junction. So there's no place for current that heads into wire 1 to go except for wire 2. It can't split off anywhere. So if we know that the current heading into wire 1 is I sub 1, we can make a judgment about the current going into wire segment 2. And again, the first thing that we can eliminate here is there's not enough information. And what we would want to apply is the law of conservation of current. So if I1 amps go into wire segment 2, I1 amps have to go into wire segment, go into wire segment 1, they also have to go into wire segment 2. So there's no opportunity for charges to go anywhere but wire segment 2. So next, the current density. So I can describe the current density for this first wire segment, J1, and compare it to J2. I know these are not going to be equal anymore because the cross-sectional areas are not equal. So I can eliminate D because we do have enough information. I can eliminate B because I know it's not tie. And when the current goes from wire segment 1 to wire segment 2, the fact that there's a larger cross-sectional area in segment 2 means that the current density in segment 2 is going to be less than the current density in segment 1. So A would be the appropriate choice here. And yeah, all we have to evaluate is the current per cross-sectional area. Now, finally here, the electric field in each of these wire segments. I know that the currents are the same, but the current densities are not the same. So if I want to compare the electric field strength E1 to E2, I can either say there is not enough information, they're both 0 because metal is a conductor, or one of my first 3 choices is correct. So if the electric field on the interior were equal to 0, that would mean that there's no force acting on the charge carriers inside of that wire, which means that the current would be 0. So we can eliminate D right off the bat. We can now take, and we also know that the electric field strength is not, I know that E1 can't be equal to 0 while ET2 is non-zero and vice versa. So we just want to figure out whether the field strength is going to be greater, equal, or less in segment 1. And what we would want to remind ourselves of is something that was mentioned in the first thought question, number 5. These 2 wire segments are made of the same thing. So their conductivities, sigma, are the same value. And we just demonstrated here that their current densities are not the same value. So if the electric field is going to be the current density divided by the conductivity, but I know that the conductivity is the same for each one. The wire segment that's got the larger current density is also going to have the stronger electric field. And yeah, all we needed to evaluate here was sigma times E. So this last bit here, this is kind of a decent place to pause with superconductivity as a concept. There's a brief discussion about this in the textbook. There's not a whole lot that we can do with superconductivity in at least this course here, but there are some materials that have essentially variable resistance to current when you have changed their temperatures. So if you could take something and then pull it down, what you would be doing is changing the conductivity sigma or I should say, and the resistivity rho. So there are certain materials that are better candidates for superconductors,